Now that we can guarantee the existence of absolute minimums and maximums using the extreme value theorem, let's figure out how to actually find the things. So the picture to keep in mind as we do this is some examples of what continuous functions on closed and bounded intervals look like. So these sorts of examples like we were looking at when we were discussing the extreme value theorem. So what we'll have to ask ourselves is, on a function like this, on a closed and bounded interval, where could the absolute minimums and maximums be hiding? Where could they be? And there's sort of two broad classes of places you might have an absolute minimum and maximum. They might be at the endpoints, or they might be in the middle somewhere. Right? It is possible for continuous functions on closed and bounded intervals to have their absolute minimums and maximums at the endpoints. So if we have a continuous function on a closed and bounded interval from a to b, the endpoints will always be a place that we'll have to check for absolute minimums and maximums. But what about if the absolute minimum and maximum is in the middle, right? So that's going to look something more like this, where there's an absolute maximum, and it's in the middle of the interval somewhere instead of at the ends. Well, something that might occur to you about this picture that I've drawn is the absolute maximum is at the top. Doesn't that mean that the tangent line there has to be horizontal? So f prime equals 0 here. Is that always the case? Well, if it's true at a maximum, it looks like it should also be true at a minimum. Looks like the derivative here should be 0. So if the derivative exists at a minimum or a maximum, then we think that the derivative at that minimum or maximum should be 0. Now, in fact, that's true, but it does take some proving. I'll save the technical details of proving that for another video. But if you're at an absolute minimum or maximum and the derivative exists, then the derivative has to be 0. So I should be a little more careful when I write this. I guess what I should say is, if x equals c is an absolute min or max for f of x, and the derivative at c exists, then f prime of c is 0. So as long as the derivative exists, if we're looking for absolute minimums and maximums, we should be looking for places where the derivative is 0. Of course, if the derivative doesn't exist, there could be an absolute minimum or maximum hiding there. So if f prime of c doesn't exist, then this x value c could still be a minimum or maximum. All right, so you can see that if we're looking for absolute minimums or maximums, there are 3 places that we have to look. We have to check endpoints. We have to check places where f prime doesn't exist. And we also have to check places where f prime is 0. These two categories, x values where the derivative either doesn't exist or is 0, these are called critical numbers. Or critical values sometimes. All right, so to find absolute minimums and maximums, as long as we're continuous on a closed and bounded interval, there has to be an absolute minimum and an absolute maximum, and it has to be in one of these 3 places. And we can usually find these things, right? In the setup for the situation, we'll know what the endpoints are. And then we can find the derivative and figure out where it doesn't exist and where it's equal to 0. And then we can just check, right? We'll know that among this list of possibilities, there is an absolute minimum or maximum. The absolute maximum will just be the biggest one, or the absolute maximum will be the x value that produces the largest output. And the absolute minimum will be the x value that produces the smallest output. So this gives us a plan for finding absolute minimums and absolute maximums. Now you might wonder, why is this better? I mean, couldn't we have just plugged in all of the x values from a to b to see which one gives us the largest and the smallest outputs? But no, we can't do that, because there are infinitely many x values between a and b. It's impossible to plug them all in and check which one gives you the biggest and smallest values. The important thing about this strategy for finding absolute maximums and absolute minimums is that usually there are only a finite number of endpoints, places where the derivative doesn't exist and places where the derivative is 0. So typically this list of possibilities will be finite. And it is possible to check a finite list of possibilities. Right? The problem with checking everything in an interval is that that gives you an infinite list of possibilities, and it's impossible to check all infinitely many places. So reducing this infinitely long list of possibilities to a finite list is what makes this strategy work.